All right, everyone. So let's start our chapter number 4, which is quadratic equations. In this chapter, we will solve a lot of real life problems, which will be quite similar to what we did in chapter number 3 actually. In chapter number 3, for example, we had situations like we have two friends. Let us say we have Rahul, right? And we have Ria over here, and there was some information maybe about their age or their pocket money. Let us say that Rahul's age is X years and Ria's age is Y years. Okay, typical mathematical example. Now, if I say that Rahul is 1 year older than Ria, right? So what I'm saying is that Rahul is one extra than Ria, right? Whatever Ria's age is, maybe Ria is 10 years old, Rahul will be 11 years old. So we learn to write this mathematically. Rahul's age is X, as we are assuming, as we have defined this variable, equals 1 plus Y. X equals 1 plus Y. So we learned that these kind of equations, as you can see, are linear because the power upon the variable is nice 1. They are linear. Highest power, the degree is 1. But they have two variables, so this will have infinitely many solutions. If I shuffle the terms, I will get x minus y equals to 1, right? And I can give you infinite combinations of x and y, whose difference is 1. I can say that 100 minus 99 is 1, so Rahul will be 100 years old because Rahul is older, and Ria is 99 years old, which is less likely, by the way. Maybe I can have 10 minus 9 is 1, right? So Rahul is 10 years old, Ria is 9 years old. So I can have numerous, by the way, infinite possibilities for this. So we learned in chapter number 3 that we need another information. And let us say this time I say that the sum of the ages is maybe 25. Okay, when I add their ages, I'm getting a nice 25. Okay. All right, so we know that we can solve them, right? If the solution exists, then it's fine. If the solution does not exist, meaning these two equations are not good enough, right? They are inconsistent if we have the case of the parallel lines. So we can solve them, right? Using substitution method or elimination method. But what if instead of this information, instead of telling you about their sum or their difference, or maybe that I doubled Rahul's age and tripled Ria's age and then add them or subtract them, instead of this, what if I say that their product x into y is 100, maybe 156? What about this? If you now proceed, and I want you to forget about this equation, this is no more here, forget about this. And if I tell you that I only have this equation number 1 and equation number 2, and I want you to solve these, okay? Let me also do it for you. So I'm going to start with the equation number 1, okay? Just like we did when solving using substitution method. So taking equation number 1, we can have x minus y equals to 1, and I will have nice y equals x minus 1, right? This is my third equation now, although it is same as the first one, but here I have nice y value. Now I'm going to substitute this y value in equation number 2, right? So put y value, okay, or you can write y equals x minus 1 in second equation. So I have xy equals 156 according to equation number 2. So this will give me x into y value, and always use these parentheses or your brackets. So you will have x into x, which will give you x square. X into this will give you negative x equals 156. Now, if this was a simple pair of linear equation scenario, I would have thus far got a simple x value. But now I have this peculiar 2 power over here, right? Yes, I know that you all are familiar with this. These are quadratic equations. And you can see it just popped up there automatically. I was just nicely solving it, and then it just popped up there, right? So these equations in which the highest power upon the variable is 2 are known as quadratic equations, right? So as you can see, it just popped up there. It happens a lot of times in real life scenarios when you are solving and making the use of the information and then trying to solve and find the value of the unknown things. You end up getting quadratic equations, right? So in this chapter, we will explore a lot of real life scenarios where these kind of equations pops up. Just to give you one simple example, let us say I have a car and it is moving with uniform acceleration like that. So acceleration is constant. And we know that in chapter number 9, we actually had three equations of motion, right? Let us say I have the first one was v equals u plus at. I hope you all remember. And the second one was s is equal to ut plus half at square. And I hope that you have noticed what I wanted you to notice. And the third equation is v square minus u square equals to 2as, right? If you look at the first equation itself, and if I assume that acceleration is constant, so this equation is going to be v, u, and a is constant, and then t. So I have three variables, and the highest power upon them is just one, and none of the variables are getting multiplied. If acceleration happens to be also changing, then this variable is getting multiplied with this variable, just like in the previous case. So this will become a quadratic one. For now, acceleration is constant, and this is a nice linear equation in three variables. But if you look at the second one, and if I assume for simplicity that for some distance, meaning my displacement or distance is constant, my initial velocity is also constant, maybe just zero. In most of the cases, we just take it to be zero. And acceleration, as you can see, is also constant. Then this equation is going to be a quadratic equation in terms of t. You can see we have t square in the last term, t, which is linear term over here, and s, the displacement, as I said, is also I'm taking to be constant. Maybe for 100 meters, I'm exploring for 100 meters, what will be the time and so on, okay, for given acceleration and given initial velocity. I'm fixing the acceleration, fixing the initial velocity, fixing the distance, and I'm trying to calculate how much time it will take. So the equation I will get will be quadratic in terms of t, right? See, these equations are popping up in our calculations. Similarly, in this one also, if I say that for some acceleration and for some displacement, I'm fixing my distance or displacement and the acceleration. And let us say I do not fix the initial velocity. So for some initial velocity, what will be the final velocity or how much final velocity I want, and so on. This equation is a quadratic equation in two variables actually, right? Right. So you can see that these equations are popping up in these real life scenarios. So that's why we are having this chapter, quadratic equations. And in this chapter, we will keep the things simple. We will learn about quadratic equations in one variable, not in two variables. And we will also have polynomial equations only. Okay, so let me give you a definition of quadratic equations. Here's a definition. The equations of the form ax square plus bx plus c equal to 0. Okay, the equations of this form. Okay, where a, b, and c are real numbers and a should not be equal to 0 are called as quadratic equations. Okay, so we have that if the equation is of this form, as you can see, it is not very difficult to understand. I'm saying that I need this term, ax square. Here, students, a, b, and c are not variables, okay? Otherwise, I'm having one variable into another variable, so it will actually become cubic, right? Because I already have 2 power over here, multiplied with another variable power, so it will become cubic. It will become cubic, right? When we multiply a variable with another variable, the degree increase, okay? The behavior of the equation changes actually. So notice here we have specified that a, b, and c are actually real numbers. Okay, they are pure numbers only. Okay, so a is a number. Here a is actually known as quadratic coefficient. Okay, it is quadratic coefficient. I hope you all remember what coefficient means. Coefficient like literally means something which is with you together, right? So a is coefficient of this quadratic term, okay? Coefficient of this x square. So known as quadratic coefficient. And this a actually is quadratic coefficient. Let me make it even more clear. This a is quadratic coefficient. This b over here is linear coefficient, okay? Linear coefficient, meaning it is the coefficient of x with the power 1 term, and this c is nothing but my constant term, okay? It is my constant term. For example, if I write 2x square minus 4x plus 3 equal to 0, this is just a simple example of a quadratic equation. Here, a value is 2. This is my quadratic coefficient. B value is negative 4, and C value will be a nice 3, right? That is my constant term. Notice, students, that in a simple quadratic equation that we are going to deal in class 10th like this, right? We have ax square, meaning we can have x square term, which should be there, right? And we can have linear term, bx can be there, right? And then a constant term can be there. So this has one power upon the variable, this has no power upon the variable. If you want to specify the variable, it will have 0 power. As you can see, the powers upon the variables are nice whole numbers. That's why I said that these are polynomial equations. I have polynomial on the left hand side and polynomial on the right hand side only, and then both of them are equated or related with each other with an equal symbol. So equal to 0. This is a polynomial equation. Okay, we are not having negative powers over the variable. We will not have, let's say, fractional power over the variables. Okay, by the way, we will learn how to solve some special non-polynomial equations. We can use some tricks, but for now, for the introductory part, we have these simple quadratic polynomial equations in one variable. So if negative powers are not allowed and it is quadratic, I cannot have x cubed term, of course. Okay, so I should have x square term, otherwise it is not quadratic. They should be linear term, right? There can be a linear term. So if I go from x square, the next term can be linear term. If this term is not here, it just does not matter. Okay, I just need x square term in my equation. As long as x square term is there, it is quadratic. And this is my constant term. It can be there, might not be. I do not care about it. Okay, that's why, students, we have specified that a specifically should not be 0. Okay, a, b, and c, they can be any real numbers. Okay, 1, 2, 3, negative 1, rational, irrational. They can be any real number. But a should not be 0. Why? Because if a happens to be 0, then this x squared term will just vanish. It will just pop out, right? It will not be there anymore. So my equation will not be quadratic anymore. Okay, my b term, b can be 0. That is not a problem. C can be 0. It can be any. They can have any real value. A also can have any real value, but not 0. Okay, if this becomes 0, then my entire thing of quadratic, because this is the only term that makes this equation quadratic, I need that. Okay, so that's why we have said that a specifically should not be equal to 0. Okay, and if I have, for example, 2x square equals 4x minus 9, so as you can see, I have a nice equation, but the terms are shuffled. So to write this in the standard form, I need to bring everything to the left hand side. So 2x square minus 4x plus 9 equal to 0, and then my a value is 2, b value is negative 4, and c value is 9. So that's it, everyone. That was a small introduction of quadratic equations. We'll catch you in the next one. Bye bye. Take care.